This conference will now be recorded.
Okay, so good morning, everyone. So this is Bharani Chandra from GMR Institute of Technology, Raja. So today we will start our discussion on buck converter, PID, and pole placement controller design. We will see how to design for a very simple buck converter, and then we will see when you want to do the real-time implementation, so what aspects need to be considered, and all those things will be discussed in the today's class. So this is the recap of the last week, whatever we have discussed, the last few days, 3 days. This is the fourth day. We started with the control system fundamentals and I did some of its applications. And then first we have designed with a gain proportional gain control. And we have seen the necessity or the requirement of the closed loop control. And then we have gone for the PID controller, some theoretical aspects we have seen, and at the same time we have seen some numerical examples as well, and then we have designed it for the uh, DC motor as well, and then the open loop analysis of DC motor and the PID controller design using auto tuning. We have manually seen the effect of KP, KI, KD for a simple transfer function, and then we have seen how we can use the automotive or automated auto tuning method to tune the PID controller for a DC motor. And then we have seen the pole placement controller. Yesterday we have discussed the pole placement controller for DC motor with and without integral action. So I would like to know how many of you have finished the pole placement controller design for DC motor with and without integral action. Could you please put it in the chat box? How many of you could at least one pole placement controller design? Either it could be the without integral or with integral, or both. Can you please put it in the chat box? How many of you have completed this one? Okay, 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 good. Good, nice. Okay, yes, but I need a clarification of symbol link modeling. Yes, good. With integral got is but not as shown. As okay. So that is good thing that some of you have actually could able to replicate the things what we have discussed in the class. So exactly if you follow the video, then it is everything has been discussed in the video. You might be doing some small mistakes, so that's why you couldn't able to uh, get the same results what I could able to get it. The reason is you might be doing some small mistake. Please try to debug yourself. Why I want you to do, because if I give everything, I can give the code as well. But once this FDP is over, then you should be on your own. So that is actually the purpose of this STP. So it's not like that if I give you everything, then it is very easy for you to just run it. But the learning, so the important thing what I want from you to do is the learning. So the learning will be missing if I give you the complete code. And this is a good opportunity for you to discuss. If you have any queries, you can discuss in the forum as well. Though I have not kept the forum open due to some reasons, because some arguments were happening among the participants itself. So that's the reason I kept it closed. But yesterday I opened it for the discussions. Okay, so leaving apart. So today we will have the discussion on the PID controller and the pole placement controller for the buck converter. The concepts, the derivations, or the equations, whatever we are discussing now, if you follow carefully, you can easily replicate for the boost or the buck boost converter as well. If you know the procedure, exactly what we are going to learn now, then it will be quite easy for you to replicate the same, as far as the other converters are concerned. It is immaterial, any converters, boost, buck boost, cuck, sepic, or any kind of converters, you can easily replicate, or you can easily derive along the same lines what we are going to discuss today. So let's go to the next slide. So the first fundamental question we had to ask ourselves, what is a buck converter? Basically, the buck converter is DC to DC step down converter. That means the input of the buck converter is DC and the output is also DC. And step down means if the input is more than the output. The fundamental question is, I want 100 volts DC to be converted to 5 volts DC. I want 100 volts DC to be converted to 5 volts DC. Why? So if you could answer this question, then we can go to the next part. The answer is very simple. In most of the cases, due to the whatever be the reason, if we have from the batteries or from a series of batteries, if we have very high voltage of, let us assume, 100 volt DC, but some of the appliances or some of the real life exam applications doesn't need that much high DC voltage. For that purpose, we need for those particular applications, we need to step down. That means from the 100 volts to, let's say, 5 volts. And for that purpose, one has to use the buck converter. A very simple application is your mobile or the laptop charger. So what is happening here is, in that one, though it is DC, the actual input required for your mobile or any laptop could be DC to the battery or so on. So, but how it is happening in the mobile? You are not the charger, whatever you are using. You know, it is not storing any energy, because when the power is on, then only you could able to charge your mobile. Otherwise, you cannot. So the thing is, but what we need for the buck converter, DC input is required. But what we are getting in the supply, we are getting the AC supply. So there is some rectifier, small rectifier will be there. So that rectifier, what it will do is it will convert the AC to DC. And however, further that DC, whatever is been converted by the rectifier, need to be stepped down to 5 volts or 7 volts or whatever it may be by using the buck converter. So that is one such application. And the quad rotor. In the quad rotor, generally we carry a series of the series of batteries. So basically for the electric propulsion purpose. However, the brain of the quad rotor is a small chip, or it could be small processor like Arduino or Raspberry or so on. For those, you don't need the large amount of, or the huge amount of DC power which is required for the propulsion. You may be needing only 5 volts or 2 volts or 3 volts or very less voltage. But for the propulsion, you need very big. Let us assume 20 volts or so. So what we are doing there is, for the propulsion, we are using the same battery. From the same battery, we need to convert it to step down for the brain, or the brain of the quadrotor, or for the processor. But for the propulsion, you can use the complete pack of batteries. And similarly for the solar charges and low power devices, and there are many such applications where you need to step down, the DC voltage. So in this lecture, we'll be discussing about the buck converter model, the transfer function, the state space approach, and then PID and pole placement controller design, and we will see some real life implementation aspects as well. So the real life implementation aspects also will be. So, so this is the fundamental circuit for the buck converter. From the ages, people are using the same buck converter, nothing, no more change. So this is the input DC voltage, and this is a switch. This switch can be realized by using various devices. Generally, MOSFETs or IGBTs are the most preferred one due to the fast switching nature. And this is the inductor, and this is the capacitance, and this is the load resistance, and this is called as a freewheeling diode. So, so there could be two types of equations you could able to get from here. Once the switch is on, or once the switch is off. Once the switch is on, then the current will flow something like this, or the current can flow also like this. When the switch is on, when the switch is off, that means it is open circuit. So what is going to happen here is whatever the current stored in this inductor, it will freewheel through this diode. So that's why it is called as a freewheeling diode. We will not go much into the very details of this buck converter, because this particular FTP, or sorry, SDP, doesn't deal with power electronics, and I don't want to go into the much details of the power electronic circuits. My main focus is the control aspects itself. I assume that you have some knowledge of buck converter. If not, I will tell you what are the basic equations required for this one. But if you want, what is continuous conduction mode, discontinuous conduction mode, and so there are several modes of this buck converter. So all these things you can read from any standard textbook like Ned Mohan or Rashid, or there are some standard textbooks you can go through that one. But that is not the part of uh, this particular lecture. Otherwise, we'll be deviating ourselves from the actual philosophy of this workshop. So there are two states. Actually, the states, basically what I told, that in the last class also we discussed, uh, which are varying with respect to the time. And you can see that why we are not considering that current passing through these resistors or the voltage across this resistor as a state, because that relation is the static relation. It is not the dynamic relation. Static relation means V equal to IR is the static relation. There is no differential equations are involved in that one. However, for the states, there should be some differential equations. Otherwise, if there is no differential equations, if it is only constants, then it is going to be zero, and the left side here it is going to be the zero, and there is no use. So in general, for the electrical circuits, the order of the system based is completely based upon the number of storing elements. So there are two storing elements here, inductor and the capacitor, and hence you will be having the second order equation. So the two states what we are going to consider for this particular buck converter is the IL, the current through the inductor, and X2 is the voltage across the capacitor, and this is the same voltage across the output voltage as well. So VC equal to V naught. And the input, the control input, all of you please listen carefully. I am talking about the control input. People, please don't get confused with this VI. This is the input voltage which is going to the plant. This is not the controlled input, because this is a constant here. So the controlled input is the duty cycle. So this is whatever the switching action, the gating pulse, what you are giving to the switch is the control input. And the output here is this voltage across the capacitor or this load, Y equal to VC or V naught. So if I derive this, this is called as averaging method, the state space equations. Whatever you are saying here is based upon the averaging method. If you want to discuss, if you want to know more about the averaging method, you can refer some standard textbooks or reference journal papers. I am not going to discuss with that one. So I assume that these two equations you have obtained by using the KVL or KCL from this particular circuit at various by doing various assumptions. So the two state derivatives x x1 dot and x2 dot, you can able to get it from here. And the control input, you can see that this is the control input VD, not the VI. VI is the constant in this particular case. Okay, so this D, or the gating pulses, or the duty cycle, whatever is going to the this particular switch, is considered as the input. And this L, R, and C, they are known to us. We assume that they are known to us. And this IL, how do I get this IL? If I integrate this particular state equation, I'll be getting IL. This VC or V naught, if I integrate the second equation, I'll be getting this VC V naught, VC. So that is how the state equations have been formulated. So next, we are going to derive the state space model for this particular buck converter. You can see that two equations what we discussed in the previous slides are these two things. So x1 equal to IL and x2 equal to VC. Again, the input U equal to D and output Y equal to VC. So this is the state space model. X dot equal to Ax plus Bu and Y equal to Cx plus Du. So now when I say x1 dot, that means x1 is IL. So IL dot, this is my IL dot. When I say x2 dot, that means x2 is VC. So VC dot I'm getting from here. So what from this, what I can say that x1 dot equal to this particular term will become 0 minus x2 by L. If I multiply like this and like this, x1 dot equal to 0 minus x2 by L. What is x2? X2 is VC. So that's why this first term is coming here. Plus U is D, my control input U is D, plus VI by L. So VI by L into D. So this expression, whatever you are seeing, if you multiply this, you will be getting. So that is relevant to the first state derivative. The second state derivative x2 dot, that means this is this one, is 1 by C. Okay, sorry, here there is a typo. This is minus, it's not the minus 1 by C. I think it is 1 by C from this one. So this is 1 by C into this x1 is IL. So 1 by C into IL minus this x2 is VC from here, minus VC by RC. And there is no control input which is affecting the second state. So that's why it is 0. Okay, so this has become x dot equal to A. This is the A matrix plus B into U. And what is my output? Output Y equal to VC. So if I say that if I multiply these two, so Y equal to x2. So x2 is nothing but from here x2 equal to VC. So that's why. So now Y equal to x2, that equal to VC. So this is, so my A equation. This is the A matrix. This is the B matrix, and this is the C matrix. D matrix here is 0. So I have the complete state space model now. So once I have the complete state space model, then what I'm going to do here, then there is a process called as state space to transfer function. So if the state space model we have just seen, or we have derived for the buck converter. So if I want to convert the state space to transfer function, this is the standard formula: C into Si minus A whole inverse into B plus D. D in our case is 0. The C matrix, A matrix, B matrix, S is the Laplace operator, and this I is the identity matrix of the same size of this A. So this is a 2 by 2 identity matrix in our buck converter. If I use this formula from here, I could directly able to get y of s by u of s equal to vi by. So this is the transfer function what I'm going to get it. So in the MATLAB there is a command which we discussed yesterday as well, ss to tf. If you directly give a b c d matrices, it will if you use the command ss to tf with appropriate input and output arguments, you could able to get this automatically. And one more thing what I want to emphasize is the state space approach, or the state space models are not unique, whereas the transfer function is unique. For the same transfer function, I can have infinite number of possible combinations of A, B, C, and D. So they are called as a different form, state space forms like controllable canonical form, observable canonical form, eigenform, Jordan form, diagonal form. There are so many forms. So the state space matrices are not unique for a particular system, but the transfer function, if I convert whatever the hundreds of various state space method, state space model for a particular system, then I should get the same transfer function. So the transfer function is the unique one, but not the state space. So this is how I have got the transfer function. Transfer function, what is here? The y of s is my output, and u of s is the input. Actually, y of s is the output of the buck converter. So the step down the value, step down voltage, and this input is the duty cycle D. So the relationship between the output and input, the Laplace transforms on and the zero initial condition, you could able to get something like this. So this is the transfer function for the particular uh, buck converter. So it is quite important to see that it resembles something like with our RLC circuit. So what is the resemblance is? The first resemblance is the it is a second order system, and it has a combination of LC, RC, and so on. So the similar RLC circuit, if you see the series RLC circuit, it has some similar structure but not the same. This VI is not there, obviously, directly it is not there in the RLC series circuits or what we have discussed. However, when I say the transfer function, it should not have any variables other than S. The remaining all should be the constants. Because by definition, transfer function is nothing but it is only defined for linear time invariant systems. The ratio of Laplace transform of outputs to the Laplace transform of inputs with zero initial conditions. So what is happening here is this Vi is the input voltage which is constant. In our case, we will see we had taken it as 100, and we will see how to what are the parameter selection. So now since I have this transfer function, so you know how to derive the how to design the PID controller once the transfer function is obtained. So if you remember the very first class, what we discussed there is the first step in any of the realistic or the real life application for the design of control system is to obtain the models or the differential equation in general. So you can see that this is the way to obtain the transfer function or the model or the differential equation for any of the plants. So this is a purely electrical system. So only by using the Kirchhoff's law we could able to come up with the transfer function. However, the DC motor, what we have seen there, we have used the Newton's law along with the electrical KVL and KCL because it is an electromechanical system. Okay. So now the buck converter parameter selections. So what are the parameters for the buck converter? The first thing is our desired specification. The input voltage is the fixed. The output voltage is the desired one. Suppose if you want to change the output voltage, though this is the buck converter, so hence the output will always be less than the input because it is stepping down. So what we have assumed that the input voltage is 100 volts and the desired output is 30 volts. So the 100 volts is the input and the desired output is 30 volts. So now in the other way, I can say that there are two ways to achieve this one. One is by using the static control law, and the second one is by using the dynamic control law. Both of the things we will discuss in very detail. What are they? And the switching frequency, what I have assumed here is 50 kilohertz, and the maximum voltage ripple, what I can allow for my in the voltage, the output voltage is 50 millivolts, and the current ripple, I can say that it can be 0.5 amps. Ripple means the variation. Suppose if it is let us assume if it is 30 volts, so 25 millivolt on the upper side and the 25 millivolt on the lower side, that band whatever I'm saying, that I can say it in, that I call it as a ripple. So it should be 30.5, it should not go beyond 30.005 volts or so on. So the duty ratio, so these are the for the design. So these things is our
Change, sir.
assumptions or
Sir,
yes.
sir, how the switching frequency is selected as 50 kilohertz,
So
sir?
this I assumed, sir. This is I assumed based upon the MOSFET what I have, based upon the available MOSFET. I assume that my MOSFET has the switching frequency of 50 kilohertz, and generally this will be given by the what I can say that supplier, whoever is supplies in the data sheet, you can get that one. Okay,
Okay, sir.
so the duty ratio is V naught by V in. So V naught is 100, sorry, V naught is 30 and V in is 100. So that's what I'm getting the duty ratio of 0.3. Always, the one thing one has to remember that duty ratio will always be between 0 to 1. The fundamental formula for the duty ratio is T on by T on plus T off. So the maximum value will go equal to 1 if T off is 0. That means T on by T on that equal to 1. And the minimum it can go to 0 as well. So generally the duty cycle will vary between, not generally, always between 0 to 1. And this is the way to calculate the L and CF. So these are standard. If you can see some of the standard textbooks or reference papers, so you will get the design formula. This is the formula, and this formula, the all other parameters are given. Like V naught is given here, VI is given here, IR is given, FS is given, VR is given. Everything is given. So if I calculate, if I substitute all these values here, then I'll be getting the inductance value as 840 microhenries. Similarly, CF, this is a capacitance. Just to avoid with why I have represented with CF is just to avoid the conflict with our state space matrix x dot equal to x plus b, y equal to cx. So C has been used there. So I don't want to use C for the capacitance. So that's why I am representing it with CF for the in the code as well. If you represent C for the both the output matrix as well as for the capacitance, then you will be in big trouble while doing the coding. So I have represented with CF. This is again the formula. So CF of the substitute, I'll be getting 25 microfarad. So what this, if I substitute the duty cycle of 0.3 and my inductor value of 840 and the CF as the capacitor as 25 microfarads, then it will ensure that the my step down voltage will be 30 volts. However, the problem here is, suppose if I want to dynamic, this is a static case. Okay, always if you want 30 volts, then that is fine. Then you can use this particular, you can use the duty cycle of 0.3 always, and you can able to get the 30 volts. However, for certain applications, sometimes I want 5 volts for one particular application, and for some application I want 10 volts, 20 volts, 30 volts, and so on. So I cannot change the always these parameters. I cannot keep on changing for my practical system this L value, CF value, and so on. So for the design, if I want to have the change in the output voltage, then always what, so I have to select this L and CF appropriately. So I cannot always keep on changing based upon my desired output. Suppose if I want 30, okay, this one 40, 50, 60, I cannot keep on changing. So if you know that it is fixed, always I need, let us assume, 5 volts itself, then you can go with the static control. So static control design, this is the static control design, and I will show you how to implement this one as well. However, if you want the dynamic desired outputs for at various instants for your particular application, then this method, this design will not work. For that, we have to go for the active control, which is the PID controller or LQR controller. So just give me a minute. Who is this waiting for name? Somebody is there with waiting for name. Okay. Okay. So now whatever I have written there, the same thing I'm going to code in this particular file. I will explain you this particular file. Let me zoom this one. So this is the parameter of buck converter. So clear all, CLC, close all. It will clear all the variable. It will clear your screen, and it will close all the figures. The input voltage is the 100. Output voltage is 30. And sampling frequency or switching frequency, it is not sampling, it is switching frequency, is 50 kilohertz. So that's why 50 into E3. Whenever you see E, that means into 10 to the into 10 to the power of 3. E minus 3 means into 10 to the power of minus 3. So the voltage ripple I want is 50 millivolts. And IR, the current ripple, I assume that it should not be go beyond 0.5. And load resistance I assume as R equal to 1. and this is the duty cycle. That's what I'm saying for the open loop control. So this is the open loop control. So V naught by Vi, and the L, the formula, whatever we have seen, just I have coded here. And the ABCD matrices also what we have seen there, I have coded here: A matrix, B matrix, C matrix, and D matrix. There is a small typo here, but I have corrected in the recent one. I will send you the corrected one. So instead of the DC, it will work, but the thing is just for the representation, instead of the DC motor, you can just write it as a buck, BUCK. And we have to do the controllability test. The controllability, oh, happening. The controllability test. What we are going to say that the order of the plant is second order in this particular case, and the rank of the controllability, if it is the same, then the plant should be controllable. The controllability test also being done here. So that is the part of the code. So you have to save this particular parameter file in with some name. You can give buck underscore parameters or so on. If you run this particular code, all the variables, whatever you are seeing here, it will be stored in the workspace. And now I'm going to show you how to do the open loop control and the closed loop control. So this is the transfer function what we have seen there. The same transfer function you may be knowing how to the same transfer function what we have seen uh, in the slide numbers 2 or 3. You know how to build this one. Take the transfer function block and write the numerator as I think Vi by L, and the denominator, this coefficient is 1, and this coefficient is 1 by R into Cf, and the third coefficient is 1 by L into Cf. So the important thing here is this is the input. This is not, always remember, the input to this plant is not V in. The input to the plant is control input is the duty cycle, and the output is the desired output or the step down voltage what we want. So what is this particular block? This particular block is called as a pulse generator, and this pulse generator is nothing but it will give the pulses to the particular switch. If it is an IGBT, or if it is an MOSFET. So what is the period of this particular pulse generator? The period should be 1 by switching frequency, 1 by Fs. And the pulse width, since this is in the percentage of the period, so D is the duty cycle, D into 100. So this is the things we have to give. And as soon as if I give this as the input to this one, you can see that it is very nicely, it is going to 30 within 0.02, something in between these two. That means 0.02, let's say 0.025. Something here, the system has, I mean, less than 3 milliseconds, the system has settled and it is very fine. So this is one such design. This is the open loop. So always what you can say that if you want to charge your mobile battery or something, and let us assume if this reference is 5 volts, so within 3 milliseconds it will directly reach to your the desired 5 volts from the zero. So as soon as you switch on your switch, it will take less than 3 milliseconds to reach to the 5 volts, and it will be there for the 5 volts forever. So since we have designed for 30 volts, so it will be there for 30 volts forever. The problem with this one is, as I told, it is a static control or open loop control, because there is no feedback mechanism from here. There could be several instances where we want to have different, desired output values. For that, this open loop control will not work, because this buck converter, in this buck converter, we have fixed C, L, and so on. However, if you want to change the desired output, if you want to change the desired output here, if you want to change the desired output here, then accordingly the duty cycle need to be designed based upon the particular desired output, as well as this CF and L value also need to be designed, because we have seen that CF and all L are the function of V in and V out and so on. So everything need to be changed. So however, suppose if you don't want to change these things, and if you are only interested, your application demands various kinds of outputs at various levels, not various kind, at various levels. Suppose 30 sometimes you need, sometimes you need 10, sometimes you need 40. So you cannot able to do with by using the single open loop controller, by using this only this one. provided if you can, it is possible, but you have to keep on changing the duty cycle and this R and L from the design thing. So, so next thing is what we have. I will show you that as well, how to do and what to do there. And the next thing is what we are trying to do here is it is a closed loop control. In the closed loop control, what we are saying that this plant is the same, and this is the desired reference value 30 in our case to start with. This can be, so what is the beauty of this closed loop control is, suppose if my desired output I want at 50, you just change this reference 50 and your PID control will take care. So what is happening here is the actual output of the buck converter is being compared with the reference value, and whatever the error has been generated, it is given to the PID one. This PID is bit different from the PID what you have seen here. Why? Because this what you can see that small, this is saturation block. Since I duty cycle is maximum 0 to 1 itself, so I don't want my PID to give beyond the 0 and 1. And this is the comparator. This is the relational operator, and this is the sawtooth one. So I'm trying to generate, this is a kind of pulse width modulation. If you want more details, you can refer Google the pulse width modulation. As again, I'm telling this not the power electronic SDP. I'm not going into much detail. So this relational operator, based upon it, will compare these two signals, and accordingly it will give the input to the plant. So in this one, so what are the changes you had to make here is uh, these are the three things in the PID controller. Sorry, to start with, this is the repeating table or the repeating sequence block. In the repeating sequence block, what I'm saying is input is 0, and one parameter is 0, the another is one way switching frequency. Then it will repeat after each of the sequence frequency, and the output will be 0 and 1. It will keep on repeating this one. And the blocks, what I'm seeing here is the PID block, the 50 and 100, and the filter coefficient is 100. This is the what I have taken, and it is giving that very good result. And and here in the PID there is another option, this PID advanced. So in the PID advanced, I'm keeping the upper value saturation limit as 1 and the lower as 0, because that is what my duty cycle will vary. I don't want to go beyond that one. So this is happening here. So what I can say from here, that if you use the PID control auto tuning, it will not work in this particular case. There may be due to the several reasons. One such reason is because it has a lot of non-linear terms. This is non-linearity, and this is non-linearity. Due to that, it is not working. So based upon the intuition, or based upon there are two things. You can completely remove these two things, these two blocks, and try to design, some controller, PID controller, and then later you inject these two parameters, and then you have to please tune this manually to get the desired response. So that is the way to do this one. If you remove this thing, it will perfectly, the auto tuning will work. Due to these two non-linear elements, the auto tuning is not working. However, remove this one and try to get some values, and further you inject, you place these two elements back, and then do the manual tuning. To the first tuning value, should you can take it from the what you have got from the auto tuning without these two blocks. Okay. So now what I can see here is, this is the comparison of the open loop and the closed loop controllers. So you can see that this is the left side. The left side is the open loop and the closed loop for the reference of 30. That means I want the output voltage, the reference is 30. You can see that open loop is working fine. That's what we have seen, and the closed loop is also working fine here as far as, but it is pretty fast as compared to this open loop. You can see that it has reached to the maximum value, very very small time, maybe 0.1 millisecond or so on. And here my requirement is that after some time, what I want is, I don't want the 30 volts anymore. My application demands the 40 volts. But the poor open loop buck converter, whatever we have designed, it cannot do anything because it has already been, everything has been fixed. So so still it is fixed here. Although my demand is 40, it is giving the same response because nothing we can change. There is no feedback mechanism or anything is happening. No, we are not doing the design as well from the scratch. However, the same, buck converter, if we use the PID controller, so you can see that, in the 40, if the reference is 40 also, you could able to get the same, you could able to get the desired output. So this is the one. So now what I will do is I will show you the demonstration and how to do this one. And then I will share you the video as well. You have to do on your own. I will close all the old one. Yeah, this is the parameter file. If you want, you can zoom your screen because I cannot do anything as the MATLAB is running here. So this is the same code what we have seen there. Now you can see that here I have changed this buck SS, whereas in the earlier one it was DC motor SS. So that doesn't matter. It doesn't reflect anything significantly in your outputs, but it is only the naming, only the names we are using. So, but wherever DC motor is there, you just change it to buck. So, so as soon as I run Scholar, who is this Scholar? Okay, so let me run this code first. So if as soon as if I run the code, then it will show that the plant is controllable. You can see that it is still running. This is the old one when I ran the code some time back. But now I ran the code again. So you can see that it is taking some time, though it should not take because parallelly I'm running several apps here. Yeah. So now you can see that the plant is controllable. And once if you run this file afterwards, what you can do here is, and this is the file what I have shown. For the simplicity, what I did here is I kept both the open loop control as well as the closed loop control here. So here the reference value I will give the first one is the 31, the design for which we have designed the plant. Okay, so this is what. So from where you will get this pulse generator, you go to the Simulink and go to the sources. In the sources, there will be this pulse generator. If you couldn't able to get any of these things manually, you just type here the pulse generator and it will show you. So this is if I'm adding this one, you can see that by default values are 1, amplitude is 1, the period is 10, and the phase pulse width is 5, and so on. But this is not the one what we want. We have to change the parameters inside this one. So what I have changed here is, so I have changed the amplitude as 1, period as 1 by fs, and the pulse width is d into 100. And this is from our design specification. Okay. And this is my open loop control. And for the closed loop control, this is the PID. So you can see that the 50, only I'm using the P and I only. I'm not using the derivative gain because it is not required in this particular application. So proportional gain is 50 and the integral gain is 100 I have selected. And okay, so another one thing I would like to show how to get the output to be saturated. So the upper saturation limit I kept as 1 and the lower saturation as 0 because that's what the maximum and minimum value of the duty cycle. And this is the repeating sequence. Again, what I have shown 0 and 1 by fs and 0 and 1. So it will repeat after every interval, whatever been discussed there. And this is a relational operator. So from where I will get this relational operator or this one, the repeating sequence again from the sources. So you can see that this is the repeating sequence. So the pulse generator and the repeating sequence, it will be from the sources. And relational operators, so I can see it could be from the this logic and bit operation because that's what the relation operator it will show. Yeah, so this is the relation operator. From the logic and bit operations you can get this relation operator. So this is the relation operator. So now what I'm going to do here is I will run this one. And first, since I ran that what I can say that that parameter file, all the variables will be stored in the workspace, and then this will be called, and this whatever the variables here, it will be called from the workspace accordingly. So now this whatever this duty cycle we have hard coded and we have fixed it for only uh, 30 volts. Desired value is 30 volts. So now if I run this one, hopefully it will run. Yeah, it is auto saving and it is trying to run. And see, one more thing importantly, you don't have to run for the default case of 10 seconds, because this is the power electronic devices, and settling time, everything should be very fast. It should be in milliseconds or the microseconds. So that's why no point in running it for 1 second or even 10 seconds. So that's why here I am just trying it for 0.01 second. And you can see that if I am opening it, so you can see that very beautifully it is going from 0 to 30. That's what we have seen in the results, to 30. And my PID controller one, you can see that it is also going to 0 to 30 in very less time. Though there is a small overshoot, but that is fine. That is very small, maybe less than 5% or so. So now the beauty of this particular closed loop control, which I'm going to demonstrate now, let us assume I want now the reference input as 40. Sorry, the desired output as 40, which I will set it as a reference value. If I run this one, I cannot do anything with this one. Since this is open loop control, there is no open loop hard coded control. So I cannot do anything here. Since I gave the 40 here, you can see that now it has gone to 40. I can show you this by running a tiny code as well. I don't know whether here it is there or not. Plots code. Yeah, yeah, this is the one. In the both thing, if you see, the reference voltage is it has been interchanged. Actually, the red one and this legends have been interchanged. Whereas obviously you can see that this is the reference one and this is the output. It is not going to 40. Whereas this has gone to 40 as well. And similarly, I will show you for very large variation as well, or very small variation as well. Though the same PID controller will not give you the exact this whatever the performance you are seeing for 30, difference of 30, because it has been designed for 30, and we are expecting that it should work for a wide range from 0 to less than 100, because 100 is the maximum, 100 is the input, so the output should be less than that. Let's see what is going to happen if I run it for 50. I had changed this to 50 and I am running it here. Hopefully this should work. You can see that how smoothly it is going to 50. And if I run again the code here, you can see that it has gone to 50 in a very less than zero point 0.5 milliseconds or so. So that is the beauty of this closed loop control. So now what you have to do here is I will share you this video recording of this one, and then you have to do on your own these things. I will share you the slides as well as the video recording of this one, and you have to do. But after this, I will tell you what I will be discussing after this particular. Once if you are done with that one, since we have gone for the very simple transfer function now after using several assumptions and so on. But for the practical consideration, you cannot always assume those considerations or those assumptions. So next, we are going to replicate some realistic, instead of the switches, instead of the exact answer function, we are going to replace with this is the MOSFET module and this is the actual diode and this is the LC and actual things, and then we'll see how it is working. So for the time being, just don't think about the thing what we are going to discuss after some time. Please go through this open loop and design the open loop and closed loop. So now it is approximately 11 o'clock. So by 11:30 we'll meet. I'll be sending you the files now, both the files in the video file as well as the PDF, and yeah, these two I'll be sending. Please complete.
ఇటు తీసుకురా
Okay, welcome back. So how many of you could able to simulate open loop or closed loop? Hi, sir. After the relational operator, there is error on data type mismatch. So I used data type converter, but you have not used. What am I missing? I changed the parameter settings in the settings. So that is there is one way to do that one. So I want you people to explore. There are many ways. So one such way is in the configure parameters. You can reset that one. Otherwise, there is a problem with double and boolean. Yeah, I know that there will be issues. I want you to debug. Once a solution is, uh, you have to, yeah, you have to in the configure parameters. You have to do some changes in the settings. I hope the open loop control at least you could able to run. Google it. The solution will be there. At least 4 5 such solutions for this problem is there. Okay, so let's start our discussion. It is 11:30. So I told that at 11:30 I'll be starting the session. This is yesterday's one. So both are done. Yes, Venkata Raghavendra. Okay. So you use some, okay, data type converter. Okay. Maybe double and boolean. You might have used some converter there. Yeah, Venkata Raghavendra. Okay. Okay, guys. So let's welcome back. So now what I'll be doing here is where I have gone. Yeah. Okay. So yes. So the next thing what I'm going to show here is a bit the control is not working. What I'm going to show here is some realistic aspects on open loop buck converter. So the realistic aspect is instead of only the transfer function, what we have used, it is a very simple one. We have used the MOSFET here and the diode here, inductor, capacitor, and the load, and this is the voltage input. Instead of some numbers, we have used some physical blocks here. The same whatever you are seeing here, you can easily implement in the PSpice as well. So the it is only the whatever the transfer function has been replaced with who is this caller 22 caller 76 all callers I'm just using. Who is this caller 89 79 and other things? Please keep your names, otherwise, Okay. So, okay. So this is the MOSFET, which is a high frequency switching. Switching action is possible with that one. And this is a diode. I will show you how to use this one. And if I run this particular uh, Simulink diagram, we will be getting the similar one. So which actually this red and blue, the labels here got interchanged. This red is actually the reference one, and this blue is the actually the output voltage. So it got there is some typo here. They got interchanged. So when I use the MOSFET, so these are the some of the parameters what I have selected. FET as 1E minus 3, internal diode resistance I have, inductance as 0, and these are the some of the parameters which you have to reset. And for your kind information, there is in the MATLAB, there is a demo block is also available for this buck converter in this particular whatever you're seeing is. But this is a bit different from in several aspects because they have used some PWM, and here directly they are generating the pulse width modulation. And the converter, that PID control strategy is also a bit different. So, so this is the one. So if I run this one, so this is the same pulse generator what we have used. If I use the same thing and if I replace the transfer function with this particular block diagram, this block diagram is the same what we have discussed. Yeah, this is the one. You can see that switch is connected to the inductor and the diode is connected, capacitor and the resistor, the load one. The same thing has been implemented. The switch is now the IGBT, and this is the actual diode one, and this is the inductor and capacitor. So, so this is the one. So for most of the, so these are the some of the parameters what I have selected for this IGBT and diode. If I run, I will be getting this thing. The same thing I have replicated by with using the PID as well. The remaining everything is the same. The only the circuit, the transfer function what you have considered, the transfer function has been replaced with this particular electrical circuit with MOSFET and electronic circuit with MOSFET and diode and other. So this is my response. So now what I'm interested here is I'll be showing you the simulation. That is opening. So the same thing what I have shown, and I will show you. I will tell you from where you can get all the block sets. I recorded the video as well. I will send you that video as well.
Hello, sir.
Yeah, hello.
Hello, sir.
Yeah,
Sir, I am
please tell.
Notan,
Hello.
sir.
Yeah, please tell.
Sir, in the previous question, you have told that you have converted the this circuit into transfer function, no, sir.
Yeah, yes.
After in the circuit, in the transfer function model only, open loop to closed loop, you have converted, no, sir. Next step, in the next step, if you convert the transfer
Open.
function into open loop to closed loop, the closed loop will changes the circuit, no, sir. Again,
Sorry. No, here the circuit is the plant is the same thing. The plant we are not changing. The whole structure, feedback structure, we are changing by introducing the PI controller.
that does not change the circuit, sir. Original circuit.
No. Circuit is original itself. That's what you can see from this, whatever now I'm showing you. The circuit is the same. R, L values will be the same only. I will show you now. The circuit will be the same.
Okay,
Only
sir.
the controller is getting changed. Yeah. I think it is, yeah, it got open now. So it is now okay, fine. Yeah. So Nutan, you can see that this L value, this R value, these are all the constant. This I'm not changing. Only I'm changing this reference voltage here. Okay, so guys, so this is this one. So some of the important things here is, suppose if you want to select this MOSFET, just go here, and as soon as if you type MOSFET, MOSFET, enter, there will be hundreds of MOSFETs here, but the one what you have to select here is this one, this tiny MOSFET which is in the black color. If you want to use the IGBT, you can use the IGBT as well, insulated gate bipolar transistor. which has the properties of both BJT and the MOSFET if you want. So this is the one, so which we'll be getting. However, inside these things, you have to use, I have used some of the parameters, what I have shown in the slide. So the same thing, I'll be sharing the slide as well with you. So yeah, so these are the parameters. The same thing you have to keep for this MOSFET. And for the diode, so this is the diode. So just again go here, and if you are, it is all from the sim power systems, you can get it, but still if you're new to this one, just type the diode here. You will get lots of diodes. And more specifically, you have to select this diode. You can see that this diode and this diode looks different. However, if you keep the same parameter here, it will change automatically. For example, I have used this number circuit as infinity and infinity, and there are some other values as well. I don't know exactly. So it will look like the same thing if you substitute the same values what we have shown, what I have shown in the slide. So this is the way to get this uh, inductance as well. How to get this R, L, and C? So again, you go here and just type RLC, and RLC series branch. This you have to select here, and it has the options. As soon as if you double click this one, here you can select all the RLC. If you want only L inductance, you can select only inductance. You can specify the inductance value. So here, what I have specified here is it is coming from the workspace. So whatever the inductance what we have saved, it is automatically coming. And the capacitance value C underscore F. That's what we have renamed. So automatically it will take it from the workspace. And this the load R equal to 1. What we assume the same it will be going to come here. So this is the way to do this thing. So once this model has been constructed, and this is the same thing, PID controller with the repeating sequence and relational operator, and this giving and whatever the output of this one is nothing but the gating pulse to the MOSFET. And if I run this one, so this plant is the same. I'm not changing any plant. I'm just only changing this control to get the desired response. It is evaluating since I'm running this circuit. Yeah, now it is it is running. Yeah, that is fine. So now we have this design is only for 30. What I can say that 30 volts at the output. So this will give us the 30 volts. So you can see that the 30 volts. So this is 30 volts. But I want it for the 40 volts. My desired output is 40 volts. I have given the 40 here. If you see this one, it is going to 40. And if I give very large value as well, I have not checked for 80 whether it is working or not. I hope it should work with little bit change in the desired specifications. Yeah, you can see that it is working, but it has bit slow down here. The reason for this slowing down, earlier it was very fast, but now it has slowed down because the PID controller has its own limitation sometimes. The PID controller is only applicable for the particular operating range where you have designed, and we have designed it for the 30 uh, voltage of 30, and we are expecting it to operate at 80. So it is very difficult to get the same specification for that one. The solution for this one is design the various PID controllers for various operating points for various region where you think that the same PID controller is not working. In between the region, you can interpolate the KPK KD gain. So sometimes that is called as a gain scheduling, which is very much used for the nonlinear control for the nonlinear systems. So this is what. So I will check for very low values as well. I have checked for 80. Let's say very low value for of 10 with the same PI controller. Even I'm not using the derivative control, very same PI controller. You can see that it is working fine, though the overshoot is 20%, and there are some ripples here, though the ripple, there are various ways to why it's not working? There are various ways to suppress this ripple, either by using some low pass filter, and although these ripples are not that harmful because the magnitude is very less, you can see that it is varying from 10 to 10.1 approximately, so it is 1% error, so 1% is fine. And the frequency, if you see that it is not that high frequency signal as well, so that is also not a big problem. You can see that the frequency is also not that very high, it is fine. So it will be, so that is fine. If not, if you want further fine, then you can tune this PI controller to get the further smoother one. So this is the way to how to do this one. And the next thing is what I have done here is we have designed the pole placement controller as well. The pole placement controller, the same code. The good beauty of this particular pole placement controller for this particular buck converter is why the same code what we had discussed yesterday will work, because the pole locations also we are using the same pole locations, -1000, -2000. Only the plant AB values are changing and everything is the same. So what you have to do is this code, whatever you are seeing here, this you need to append with the earlier parameter code, and if you run, then it will give us. I don't have to explain this one because yesterday we explained this is the same code, and I will explain the results what is happening here, which is more important because the code is exactly the same thing. So what I want here is I am expecting my output, the desired output to be the one, the unit step. You can see that without integral action, it is giving some idiotic value of 2500 or something, which is not realistic at all. However, if I use the integral action, you can see that it has settled at 1. So which shows that within less than 0.007, 0.005 to 7 something here is the setting time. So this is far better. Then how to implement this? I'm not intentionally. I have not recorded and I have not shown here as well, because the implementation will be the very much similar to the one what we have done yesterday. The same thing, just copy paste everything the same, and if you run, it will work. Just ABCD matrices, whatever you have seen yesterday, the same symboling code will work for this one. That I can tell you. And then, but it will be in the state space thing. But when you want to convert it to the switches, what we have discussed for the PID controller, you need little bit changes in that one, which you can do on your own. So what I will do here is I will give you this slides and this code, and I will give you 15 minutes of time. You try to see if it is possible to do it or not. So we will meet shortly at 12 noon today. I'll be sharing you the links in a couple of minutes. Okay, so let's start the discussion on the tomorrow's topic. And actually, this is the end of the today's topic. So, any of you have got the results? So, though it is too quick to expect, but did any of you have got the results for this approach? How to solve data type mismatch error? Relational operator output is Boolean, but transfer function requires input double. Saurav Kumar has answered use data type conversion block and decide yes. Good morning, sir. Can I ask one question regarding yesterday quiz? That you can ask later, sir. Uh, thank you for the solution. Yes, I intentionally didn't give the solution so that you people should explore it. Yes, guys. So, anyone is having any doubts till now? Whatever we have done the discussion, because uh, tomorrow it is mandatory for all of you to attend. If you are not attending, then I am not sure you will be getting the certificate or not. So, my only request is tomorrow, please attend. It doesn't matter if you are not attempted the quiz for the last 4 days or whatever it may be. But if you are attempting tomorrow the quiz, then you will be given the certificate, graded certificate. So I'll be doing the relative grading. So that's what keep on doing from the past 3 months for the various FTPs and other things. So there will be relative grading. So based upon the marks the participants get, based upon that I'll be doing the relative grading. So my request is all of you compulsory mandatorily please attend this one. If you're not attending, then you will be losing the opportunity to to get the certificate. And tomorrow will be the concluding session. So what I'll be doing here is tomorrow I will discuss with single machine infinite bus system SMIB, the PID controller and the pole placement controller for that one. And briefly I will explain that how to do. And then since in the 4 days you might have already been experienced with designing the PID controller and pole placement controller, so that will be along the same lines itself. So it is not going to be different, completely different from what you have done till now. So, so only the plant will be changed, but there will be some small tricky things which need to be discussed tomorrow. Afterwards, from 11 o'clock onwards, 11 to 11:30, I will be summarizing in the 4 days whatever we have done in very detailed way. Though it is half an hour, I will try to capture the important points what we have been discussing in the last 4 days or 4.5 days if it comes. So from tomorrow 11 to 11:30, and 11:30 onwards. 11:30 onwards there will be a grand quiz. Sorry, 11:30 onwards there will be a valedictory for 10 to 15 minutes. As soon as the valedictory is over, I will release the final quiz, the grand quiz, which will be of around 50 questions. And exactly I'll be you will have 25 to 30 minutes, 30 minutes to write that 50 quiz, and the time will start just after the valedictory. I'm not sure when the valedictory will be over. It can be in 5 minutes, or it may take 15 or 20 minutes as well. So please, all of you, please ensure that you should attend tomorrow's lecture at sharply at 10 o'clock, and we will try to conclude. The lecture will be concluded by 11:30, and 11:30 there will be valedictory. As soon as the valedictory is over, then I will release the grand quiz questions to you. And from the time when I release, so you will be having half an hour to do the quiz. So that is from my side. If you have any queries regarding the today's lecture, so we can have discussion on that one. Otherwise, I'll be winding the session. And mind you, tomorrow I will not give you the YouTube video. I will not give you the Simulink diagram. Just I will give you the model, and I will explain you my Simulink diagram, my solution, and tomorrow you have to build on your own. That's how I have framed this HTTP in a such a way that slowly, no, slowly. Initially, I started with spoon feeding. and slowly I think you are on your own now. So that is what actually I want from you. So anyone is having any questions? So all the participants are quiet. Am I audible or not? Hello? Could could any of you please respond?
Yes, sir, it's audible, sir. You are audible.
Okay, okay. That's good because all of you are quiet. Still one more day is there. If you, if you lose your patience, if you lose your energy now itself, then this SDP is just the, catalyst. From here, you have to take on your own.
No, sir, we have a lot of energy, but there is no queries. That's why we are all silent.
Fine, fine, fine. Yeah, 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 yeah. So fine. So I think I hope that all of you have, all of you might have gone through this lecture very carefully and you don't have any doubts. That is fine. I just released the quiz. You can see the WhatsApp link. So tomorrow there will be the grand quiz. So all of you, please ensure that you should be there tomorrow at any cost. Okay. So that is my only request, and I am making it a mandate for all of you. Tomorrow you should be there for 2 hours. Okay. Okay. Then if you don't have any issue, then fine. Then all the best. So try to complete all the assignments what has been given to you, and we will meet tomorrow. I am ending the session now. Thank you.
Sir.